So that was based on baseline data only.
That's right. That's based on baseline data only.
So how can you divide IL from CR? I don't understand. It's just baseline before the intervention.
So, so I know what their randomization status is, and I've measured the rate of change in their biological age using data that were collected at all time points. So this is biological aging measured in the same way as we measured it in the original Journals of Gerontology study, using this Clameret-Duval equation applied to physiological data and how that changes over time. So essentially I'm using the output of that study to form the y-axis in this study. And what I'm asking is whether we can epigenetically predict that rate of aging from the baseline methylome. Does that make sense?
You only have baseline?
We only have baseline methylation data. You want to try it?
Let me see if I can understand this. So what you did is in Dunedin, you have an epigenetic marker that predicts how they've aged over the previous 12 months, or 12 years in Dunedin. You've taken that score and you've applied it to CALERIE. And you've said, okay, it's roughly the same age people, all that kind of stuff. It's roughly the same biological age marker. And you're saying, okay, so at baseline, I can predict what their aging has been up to this point. And we'd expect it to be continuous over the subsequent 2 years, right? And you're saying, okay, so people with the highest rate of aging, does that continue over the subsequent years? And that's what this shows on the left in the AL group. Is that right? And this methylation marker showing how quickly people have been aging previously. When you go to CR, that completely abolishes that relationship. No, the biologicals are sequential. The change in physical function, the change in mental function, the change in the albumin, the change in the CRP, the change in the whatever. That's their biological age, right? And the question is, correct.
Yeah, so again, just for everybody online, the question was, how can you study the rate of change in biological aging if you only have epigenetic data at baseline? And the answer is, we're not yet measuring the rate of aging longitudinally using epigenetic data. We're relying on the same physiological data that we examined in this original study, which is now on the screen. And what we're asking is, can we predict the results from that study with this epigenetic measurement at baseline?
If I understand you correctly, the key point is that the caloric restriction destroys the relationship that you'd expect to see, which is about 6% of the variance being R squared. And then the question that I would ask then is, what happens if you look at 12 months where you haven't started to regain? Is that effect stronger? Do you see a negative effect in the CRs?
Right, so this is a good question. If you computed the slopes of biological aging over only the first interval of the trial, would the result be stronger because the CR was stronger? I think we haven't done that analysis, and the reason we haven't tried to analyze slopes over the first 6 months is that measuring change with only 2 time points is a dicey business, because you can't distinguish measurement error essentially from true change. You need 3 time points for that. With respect to this question of does the dose of CR have an effect on biological aging, I may have a slide for you. There is one in the supplemental material of the original manuscript. And the answer, there it is. The answer is that the dose does have an effect, but not a huge effect. So here we've just binned the study members into those who were in the treatment group who achieved greater than 10% caloric restriction, and those who achieved less than 10% caloric restriction. The ad libitum are these dark blue dots going up, as we would expect. And then here's sort of weak CR, and the dark blue is the stronger CR. And to some extent, there is a dose-response effect with respect to caloric restriction.
I was going to ask if there have been naturalistic studies of changes in the Horvath measures, for example, that suggest that you're going to see a significant change over 2 years.
I planned all of this way I did.
Okay, so this is not on. Okay, so the question was, do you expect to see longitudinal change in epigenetic clocks? Is that possible? So the answer there is yes, we do, and there in fact are other data sets that have published on this. Cor Christensen in his cohort in Denmark has some data. I believe Ian Deary has put some data out there from his Lothian birth cohort in Scotland, showing that even over relatively short periods of time, people's epigenetic clocks do tick forward. These are data from the Dunedin study showing that over 12 years between two different measurements of the epigenetic clocks, the clocks tick forward by, on average, 12 years. So the clocks tell time, they tell time within person, and they can detect changes on the orders of years with relatively high precision. Our observation, though, has been that changes in the ticking rates of epigenetic clocks are only weakly correlated with changes in other physiological parameters. And as illustrated in this figure here, I'm showing effect sizes in terms of a Pearson R ranging from 0 to 0.3, so these are all small effects. This is telomere erosion based on 2 time points, and these epigenetic ticking rates for a 353 CPG clock, a 99 CPG clock, and a 71 CPG clock. And what you can see is that for all of them, there's very little predictive power for assessing balance, grip strength, motor coordination, cognitive test performance, changing cognitive test performance since adolescence, self-rated health, and this measure of aged appearance that we used in our original paper. In contrast to, this is our pace of aging measure. So it is possible to predict these parameters of function in individuals who are still relatively young and healthy. It's not clear that accelerated aging as measured by the epigenetic clocks is forecasting that, but certainly change in the epigenetic clocks is measurable.
I think we can take one more and then we have to have a break.
Sorry. No, I just want some clarification regarding the biomarker because you mentioned that. You had biomarker panel for the one that you used to measure pace of aging, and then you also have the biological age that you already done in this paper. So are those different, or I think you have different definition of biological aging here, and I just would like to know what your consideration about the approaches that you use, any discrepancies between them?
Yeah, so the Clamara-Dubois biological age is based on a cross-section of data at any given time point. So it's essentially built on a series of regression models that try to recover the chronological age of a person based on a series of measurements of clinical parameters. And it's trained by predicting age differences in people in a large data set of mixed age. So this 5,000 people in the NHANES between the ages of 30 and 75, or in our original analysis, 10,000. But that's the age variation that is the source of that Clamara-Dubois biological age algorithm. And when applied, it gives you a specific age for a cross-section of biological data. In contrast, the pace of aging is measured from longitudinal changes in these 18 different parameters, which you can't see here, several of which overlap with the Clamara-Dubois biological age. But importantly, it's only based on the changes in those parameters over time, not on their baseline level. So that's basically the difference. The Clamara-Dubois algorithm is based on the level. The pace of aging is based on within-person change. The measures are correlated, as we reported in the original paper. The correlation between those two measurements is about 0.4. So I think, I guess what I would say is that we are measuring the rate of change in physiology, producing an epigenetic algorithm to predict that rate of change, and then applying that epigenetic algorithm to predict the rate of change in physiology in a new sample. So in that sense, there is a parallelism, and that's parallelism by design. The jury is still out on whether these rates of change in physiology and rates of change in, let's say, epigenetic marks like DNA methylation are telling us the same thing. So far, based on our own comparative analysis, what we can say is that the epigenetic clocks and these physiological algorithms do not appear to be measuring the same thing.
Thank you, Dan. Thank you, everyone, for your patience. I think that was an exciting presentation of some early data, but to basically show, hopefully, the potential we still have in the calorie samples and in the data. We even used cantabs in that analysis, right? So what we're going to do is we're going to take a 12-minute break. So we can come back at 10:55, and for the web people, we'll see you in 12 minutes.
For the white people. For the white people.
Yeah, that's what I heard.